Languages and finite state machines. In this video, we will be covering the basics and vocabulary. A follow-on video will discuss finite state machines. We define sigma, a non-empty finite set of symbols collectively called an alphabet. From an alphabet, we build strings, which is a sequence of symbols a computer processes. If sigma is an alphabet, and n is a positive integer, we define the powers of sigma recursively. First is the base case. Sigma raised to the 1 is equal to sigma. The recursion, sigma raised to the n plus 1, is equal to the string xy, such that x, the first part of the string, comes from sigma, and y, the second part of the string, comes from sigma to the n. If sigma is an alphabet, then sigma plus is equal to the union from 1 to infinity, sigma to the n, which is essentially the union of all the sigma to the n, where n is a positive integer. Sigma star is equal to the union from n equals 0 to infinity of sigma n. So the difference between sigma plus and sigma star contains sigma to the 0, which is defined to be the empty string that contains no symbols. An example of string construction: if our alphabet is equal to 0, 1, we can construct the powers of our alphabet. So our sigma to the 0 is equal to the empty string. Sigma 1 is simply equal to sigma. Sigma squared is the set where we take our first element from sigma and our second element from sigma 1. Again, a first element from sigma and our second element from sigma 1. And then first element from sigma and second element from sigma 1. First element from sigma, second element from sigma 1. And you can use combinatorics to verify that we're expecting 2 times 2, which is 4 elements. We can continue sigma 3, our first element from sigma, our second element from sigma 2. So we're going to combine the 0 with the 0, 0, the 0, 1, the 1, 0, and then the 1, 1. So again, combining the 0 with the 0, 1, combining the 0 with the 1, 0, and then last the 0 with the 1, 1. And now we're going to combine the 1 with the 4 numbers. So we have 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. If we continue, we can see that the positive closure, the sigma plus, is going to give us all the 0, 1 strings, all the possible 0, 1 strings. If W1 and W2 are elements of our sigma plus, and W1 is the string x1, x2 up to xm, and W2 is the string y1, y2 up to yn, then W1 and W2 are equal if m is equal to n, in other words, their lengths are the same, and if x of I is equal to y sub I for all I between 1 and m. So each corresponding element is the same, and it's really your intuitive sense of equal strings. The length of W, denoted with this absolute value sign, is equal to n. And we have the additional note that the empty string, the length of the empty string, is 0. The concatenation of x and y is equal to, you just basically put the x string and then the y string, again, kind of your intuitive notion of concatenation. In the previous slide, we had defined the powers of an alphabet, and we looked to see what the alphabet star would be equal to, what the possible strings were. Now we're going to say, given a string in a sigma star, we're going to define the powers of this string x recursively. So our base case will be x of 0 is equal to empty string, x of 1 is equal to the string x. Then our recursion, x of n plus 1, is equal to x concatenated with x of n, where n is a natural number. As an example of both the powers of a string and length of a string, we can consider our alphabet to be 0, 1, and our string to be x equals 0, 1. So we'll start with x to the 0 is equal to the null string, and the length of the null string is equal to 0. x1 is equal to x, which is 0, 1, and the length of x1 is equal to 2. x2 is equal to x, which is 0, 1, concatenated with x1, which is also 0, 1, and the length of x2 is equal to 4. x3 is equal to x, which is 0, 1, concatenated with x2, which is 0, 1, 0, 1, and the length of x3 is equal to 6. Some more definitions. If x and y are elements of sigma star, so in other words, x and y are strings of this alphabet, and w is equal to the concatenation of x and y, then x is called a prefix of w, and if y does not equal the null string, x is a proper prefix. Y is called a suffix of w, and if x does not equal the null string, then y is a proper suffix. So kind of again, it goes with your intuition of what a prefix and a suffix would be. If x, y, and z are elements of this sigma star, and w is equal to x concatenated with y concatenated with z, then y is called a substring of w. If x does not equal the null string, or z does not equal the null string, then y is a proper substring. For an example of prefixes, let's look at the string 0, 1, 0, 1, 0, 1, and we will list all the proper prefixes. We can consider the empty string a proper prefix. Next, we can consider 0. So in this case, we're considering x, our prefix, and y over here is not the null string, would be y. Our next prefix would be 0, 1. Here we would consider 0, 1 our prefix, the x part, and then our y part is the 1, 0, 1. Then we have 0, 1, 0, which is over here. We have 0, 1, 0, 1, which is here. We have 0, 1, 0, 1, 0, considering this the prefix. And then we cannot include 0, 1, 0, 1, 0, 1 as x, because then y would be the null string. So this is it for our proper prefixes. For a given alphabet, any subset of sigma star is called a language over sigma. So the idea is we have this alphabet sigma, we construct all possible strings using the sigma star, and then we take a subset of those strings which we use as our language. And we can build, once we have one language, we can build other languages. So for languages A and B, a subset of sigma star, the concatenation of A and B, denoted AB, is equal to AB, string A and string B, where A is an element of A and B is an element of the set B. There are other ways we can construct new languages from existing languages. So for example, given an existing language A, a subset of sigma star, we can construct other languages. The first one is the powers. So we define this recursively. A0 is equal to the null set. A1 is simply equal to A. Then the recursive part, AN plus 1, is equal to the strings AB, such that A comes from our original language and B comes from a sub n. We'll do some examples in a minute. The next language we can make from A is called a positive closure. The positive closure is denoted A plus is equal to the union of a sub n, where n comes from the positive integer. And last, we have the Kleene closure, also called the Kleene star. So A star is equal to A plus union the null set. As an example, we'll look at the alphabet equal xy, and the language from that alphabet equal to xx, xy, yx, and yy. So first we're going to look at the powers of sigma and convince ourselves that that A is a subset of the powers of sigma. So sigma 1 is just equal to xy, or sigma. Sigma 2, the first part of the strings are going to come from sigma, and the second part of the string is coming from sigma 1. So we have x from sigma, and then we also have an x from sigma 1. We have an x from sigma and a y from sigma 1. Then we can work with the y from sigma, and we'll concatenate it with the x from sigma 1, and then concatenate it with the y from sigma 1. So we have the y, x, and there's no comma, and the y, y. Next, we'll look at sigma 3. Again, we're going to take our first part of the element from sigma, which is x, and then we are going to concatenate that x with sigma 2, first with the xx, again taking the x from sigma, and then concatenating it with an element from sigma 2, the xy, an element from sigma, the x, concatenating it with the yx, so our x with the yx, and then last our sigma, our x from sigma, and then concatenating it with the yy. Next, we will have to take the y from sigma and concatenate it with the xx from sigma 1. So yxx. Again, the y from sigma, and now we're going to concatenate it with the xy. Again, the y from sigma, and we will concatenate it with yx. And lastly, the y from sigma concatenated with yy. And just a note, you can see that our language A is definitely a subset of sigma star, and in fact it's actually equal to sigma squared. So now we will look at the powers of A. So we have A1 is equal to xx, xy, yx, and yy. And this is also equal to A1. To get A2, we're going to concatenate strings from our original language A with strings from A1, which also happens to be A. So again, we'll start with concatenating xx from A with our xx, xy, yx, and yy from A1. So we have xx from A, xx from A1, xx from A, xy from A1, xx from A, and yx from A1, xx from A, and yy from A1. We'll do the same with our xy from A, and we'll concatenate it with each of these terms from A1. So I have xy, xx, xy, 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 yx, I shouldn't have a comma there, yx, and xy, yy. Next, we'll concatenate our yx with each of these terms. And then last, we'll concatenate yy with each of these terms. And here we have A2. And just to start A3, we would start by concatenating xx from A with all 16 terms of A2. And then we would concatenate xy with all 16 terms, yx with all 16 terms, and yy with all 16 terms. So we would have 64 terms, which I will not do all out. And then if we look at the pattern, then our sigma plus is going to be all xy strings. Our A plus, our language plus, are all even length. Strings. So taking a look one more time, our Kleene plus of our alphabet will give us all XY strings. Our Kleene plus of our language will give us all even length strings. Next we have this theorem. Since we're talking about languages which are really formally sets, we have different containment theorems as well as containment and unions. And last, we're going to look at this notation. If you're familiar with regular expressions, this is the same as regular expressions are actually a language. So this is this comes from the regular expression language. But this first 0, 0 in the brackets means that we're talking about strings that start with a 0, 0. This Kleene star here tells you that you have any number from 0 to however many, infinitely many zeros. So that's the Kleene star, followed by 0 or more zeros, and then ending with the string 1, 0. So an example of a string that fits this description would be 0, 0, 1, 0. That's when I decided to have 0 zeros with this Kleene star. Or it could be 0, 0, and then for the Kleene star I could just add 1, 0 in the middle, and then 1, 0. Or I could decide to add 5 zeros in the middle, in which case I would have 0, 0, 1, 2, 3, 4, 5, 1, 0. So all of these strings satisfy this condition of this notation here. So in this video, we discussed vocabulary of languages and we're set up to do finite state machines in our follow-on part 2 video. Thank you for listening.